Okay, good afternoon. We're going to continue talking about monotonicity of demand and related results. I mean, results related to the conditions we have found that imply monotonicity. Well, one auxiliary result, which is interested in itself, is the following proposition. Which is examining the consequences of the utility function being continuous. Does continuity of U imply continuity of the indirect utility function? Not at all. But we have this result. If the utility function is continuous, then we have V of P equal to the limit as alpha goes to 0 plus of V of P plus alpha D for every PD in R plus N. This is almost directional continuity, but it's less than that because it's alpha going to 0 plus, not to 0. Okay? Then, so it implies something, but not much. We are going to use this result later in our analysis of the conditions related to monotonicity of demand. So, and let us give the proof of this result. First of all, observe that we know that the indirect utility function is always non-increasing. So this, as a function of alpha, is non-increasing. Therefore, the limit is the supremum. So equivalently to lib, you can write, if you prefer, supremum over alpha strictly positive. So we are going to prove this equality by proving the two inequalities. And the fact that the left-hand side is greater than or equal to the right-hand side is immediate because P plus alpha D is larger than V of P, V is decreasing, and then because lim is supremum, we have the inequality in an immediate way. Now let us prove the opposite inequality. And for this, consider an arbitrary positive epsilon and take y. In R plus N, close enough to, well, it's too early to talk about epsilon positive. So to compare with the right-hand side with V of P, I have to deal with V of P, and so I have to consider an X in R plus N such that Px is less than or equal to 1. Okay, I consider a feasible X for this praise vector. Now, take Y close enough to X, to that particular X, such that Px is less than 1 and U of Y is greater than U of X minus epsilon. Okay, this exists by continuity of U, and the fact because but P of X is less than 1. So this means that we can take this. No, there is no problem because I move. So we don't know if this is satisfied with the equal sign or not. But close enough to this point, there is another point Y satisfying this condition, and the problem might be if Px is equal to 1. If Px is less than 1, there is no problem for the existence of that Y. But if P of Y of X is equal to 1, it may be that, so this is Px equal 1. Here is our X. Then it may be, so around this point, everything is greater than U of X minus epsilon in a neighborhood, then no, there is no problem. This happens even if we are restricted to this part. So everything was okay. I was thinking that there might be a problem, but it's not the case. Now, take alpha naught, strictly positive, and small enough such that this is Y, okay? So I had X, and I am taking Y, satisfying this strict inequality, and close enough to U of X to be larger than U of X minus epsilon. Now I take epsilon alpha naught small enough such that P Y plus alpha naught D is still strictly less than 1. Okay, no problem. I am here, I move a little bit in the direction of D, and then I'm still in the same half plane. Now, let's look at that limit. The limit as alpha goes to 0 plus of Vp plus alpha d, because it is the supremum. In our situation, lim is the same as supremum. This is greater than or equal to the particular value corresponding to alpha 0, alpha naught. Okay? No. Here I am not moving from y, I am moving from p. Because I need to consider v of p plus alpha naught d. And under this price vector, y is feasible. So it satisfies the budget constraint with a strict inequality. So this is greater than or equal to u of this particular y, which was taken to be greater than u of x minus epsilon. So since epsilon was an arbitrary positive number, then we conclude that the limit as alpha goes to 0 plus of b plus alpha d is greater than or equal to u of x, and x is any feasible commodity bundle after p. So this means that this lim is greater than or the supremum of all these values for x feasible under p. And that supremum is what we have called v of p. So we have got the opposite inequality, and therefore we have proved the equality. Okay, to move from here to there, we have made this step many times. If you want, make epsilon go to 0, 0 plus. As I said, we will use this result later. Now, another useful result is the following. Just a comment, we are dealing with direct and indirect utility functions, but the indirect utility function is just the optimal value function of a parametric optimization problem. So the techniques, the ideas we are using here may be useful for other parametric optimization problems as well, with a similar structure. Okay, then the proposition we are going to prove next is suppose u is a regular, slightly more than regular, utility function, quasi-concave, non-decreasing, and not only upper semi-continuous, but continuous. Then, under this assumption, what can we say? What are the conditions for the indirect utility function to be convex? And what's the interest of this proposition? So remember that we said that a sufficient condition for monotonicity was that the function psi px given by u of x minus v of p, this function be concave, quasi-concave, quasi-concave. And that for this function to be quasi-concave, which is a separable function, is a function of x plus a function of p, we just need one of the functions to be concave, and the other must be just quasi-concave, but not too far from being concave. I never gave the details, but there is the notion of index of non-concavity, and the result by Jean-Pierre Crouzet says that if the index is of non-concavity is not too high, then the function would be quasi-concave. Okay? So then this situation is what motivates this result. We assume that U is just quasi-concave, but we are not talking about its index of non-concavity, but just consider quasi-concavity. And then we are interested in conditions for minus V to be quasi-concave, to be concave. Okay, to be concave, which means V to be convex. Okay. By the way, I have not talked about the index of convexity, but it's related to compositions with exponential functions. I don't remember now the precise definition, but it's something like you raise your function after multiplying with an index with a constant r to the exponential, maybe with minus here, and then you look for the r's such that after this composition your function is convex. And then you take the optimal r, let's say. We have to think, I don't remember now the signs, if you need a sign here or not, and then I don't remember if you take the supremum or the infimum. But this is the idea. How far your function is from being convex depends on the r's that work here so that they make it convex. Good. Now, under these conditions, what is a necessary and sufficient condition for convexity of the indirect utility function? Any intuition? I was telling you that all these results are unpublished, but this is. But it will be very hard for you to find it because it's in a volume that was made in a Spanish university, University of La Laguna, in honor of a friend of mine and co-author, Antonio Martinon, long ago when he turned 60. So I sent this article to that volume and it's there. I don't know if it is available online. I have an electronic copy if you are interested, but this particular result is published. So any intuition about the equivalent condition for convexity? No. I mean, forget demand. So what are the conditions on U, assumed to satisfy all these assumptions? Necessary and sufficient conditions for U that for V to be convex. I'm asking you just to see if you have some intuition. If you have, I congratulate you because I don't. I mean, I had it because I produced this result, but I don't remember what was my intuition at that time. Now I can give you a formal proof, hopefully with no many troubles, but no idea? Sorry? B is always quasi-convex. But now we are interested in much stronger property, convexity. So what else has to be imposed on you to get a convex indirect utility function? And the answer I will give you is if and only if. Preferences, don't talk about preferences, talk about you. Now you have utility functions. I will give you the result, but don't ask me about a geometric intuition. You can ask me about the proof, but not about. So, the condition is that the function that to t strictly positive assigns u of x over t is convex for every x. I am of your opinion, but I had it long ago. I mean, or I don't know how I forgot how I reached this condition, but now to me it looks as mysterious as it looks to you. Maybe I was sleeping and, and it came in my dreams. No, maybe it's not so, I don't know, when some results may look surprising, but when you try to find out, you obtain them. Maybe this is the case, I don't know. Well, so which implication do you want to see first? Let's try to prove this implication first. Okay. So, but first a comment. Notice that this is a convexity property along rays. So we fix 1x and consider what happens for x divided by t for this given x. Then this function happens to be convex on every ray. It's a property of convexity along rays, although it's not convexity along rays, because convexity along rays is when t is multiplying instead of dividing, okay? Then, first of all, I will use that because u is regular, even more than regular, because it's even continuous. Upper semi-continuous would be enough. Then u of x is equal to the infimum of v of p subject to px less than or equal to 1. Okay. Without the validity of this formula, it would be quite difficult to move from right to left, because we need to obtain conditions on u from conditions on v. So without this formula or another formula giving u in terms of v, it would be quite hard. Okay? But now we have this situation. So let's prove that, let's fix x in R plus n. And let's prove that the corresponding function is convex. So I take t prime strictly positive numbers and lambda between 0 and 1. And then I take epsilon positive, arbitrarily small. I consider x divided by t and x divided by t prime. And I'm using this formula for both x divided by t and x prime divided by t prime. So I have to consider p's that are compatible in this sense with x divided by t and with x divided by t prime. I call these elements p and p prime. So I consider arbitrary p prime in R plus n. P is compatible with x divided by t, and p prime is compatible with x divided by t prime. And not only that, I take those p's, p and p prime, as close to the optimal, or so that their values are as close to the infimum as I want. Actually, that the difference is smaller than epsilon. So I choose this p such that v of this p is less than or equal to the infimum, which is x over t plus epsilon. Okay, but the definition of infimum and the fact that the infimum, when I write here x over t, is u of x over t, then this is possible. And then we want to use convexity of V. So I consider 1 minus lambda p plus lambda p prime, and I multiply it with x, our x. This is 1 minus lambda px plus lambda p prime x, but px is less than or equal to t, and p prime x is less than or equal to t prime. So this is less than or equal to 1 minus lambda t plus lambda t prime. That is to say, 1 minus lambda p plus lambda p prime. Remember that t and t prime are both strictly positive. So this convex combination of them is strictly positive too. So I can divide here by 1 minus lambda t plus lambda t prime and get that this is less than or equal to 1. So this commodity bundle is affordable under this price vector. So what can I say about U at this particular x divided by 1 minus lambda t plus lambda t prime? I can say that the value of U at this particular point is less than or equal to the optimal value for these prices. And the optimal value is what we call V. So this automatically follows from that. When you have P and X such that Px is less than or equal to 1, automatically U of X is less than or equal to V of P by definition of the indirect utility function. Okay, so this is what I was considering this, that now I can apply convexity of V, which is our assumption. So V of this is less than or equal to the corresponding convex combination of V's. V of P plus lambda V of P prime. But remember how we chose V of P and V of P prime. Then, because 1 minus lambda and lambda are non-negative, this is less than or equal to 1 minus lambda U of X over T plus epsilon plus lambda U X over T prime plus epsilon, which is equal to one minus lambda U of X over T plus lambda U X over T prime plus epsilon. And now, because epsilon is an arbitrary positive number, we get U of X over 1 minus lambda T plus lambda T prime less than or equal to 1 minus lambda U over X over T plus lambda U X over T prime, which is exactly the convexity condition for this function. Is it okay? So do you agree with this proof? So let's try to prove the converse. So suppose our utility function has this convexity along rays property. Let's prove that V is convex. Just a comment, each proposition of this type has a symmetric version, interchanging U and V. Because here what I am using is that U is regular, and then thanks to this regularity, U can be expressed in terms of V. but V can always express in terms of U. So you could get a condition of the type U is convex if and only if the indirect utility function has this property. Okay. Another comment. U is quasi-concave, okay, but here, okay, it is in the denominator, but then it's convexity, nothing like quasi-concavity or concavity. It's convexity, but within the denominator. So, assume that that convexity along rays is satisfied, and then let's try to prove convexity of V. So, let P and Q be in R plus N, and lambda belong to the 0-1 interval. Because I need to deal with V of the convex combination, 1 minus lambda P plus lambda Q, I have to consider a commodity bundle which is compatible with that convex combination. So I take X, I consider an arbitrary X such that 1 minus lambda P plus lambda Q times X is less than or equal to 1. Okay? So I have to end up proving that V of this convex combination is less than or equal to the corresponding convex combination of the values. We will see that this is always the case. So, first of all, if X equals 0, if X is equal to 0, we have U of 0 less than 1 minus lambda V of P plus lambda V of Q. Okay? Is this clear? Just in case. U of 0 is equal to 1 minus lambda U of 0 plus lambda U of 0. No doubt about it. But 0 is compatible with every vector, with every price vector, in particular with P, because it's for free. Then this is less than or equal to 1 minus lambda V of P plus lambda V of Q. So we want to prove that this inequality holds not only for 0, but for every X satisfying this condition. I have to distinguish the case when U is equal, X is equal to 0. So now, consider the case when X is different from 0. Satisfies this condition. Then, again, I have a technical problem here, but I hope it will not be so difficult to solve. Probably instead of distinguishing between the case when it is 0 and it is different from 0, because now I have a little technical difficulty to continue, I have to consider the case when x is not in r plus n, when it is not strictly positive in all of its components, or it is. The proof that of the general case has no or. I don't know, we have to think a little bit. So, will this work for x non-extremely I think we have to find to discuss about relations between P, Q, and X, which an observation which I didn't notice yesterday when preparing this proof. So I want to have, for continuing the proof, what I need is that the minimum between Px and Qx, or the maximum between Px and Qx, to be strictly positive. For the proof I have of this case, I need this condition. So I need at least one of the two to be strictly positive. So maybe the proof here can be adapted to the case when x is not here, but both, let us see, Px and Qx are equal to 0. Yeah, then it works. So I think I have succeeded to repair this proof. You will tell me if I am right or no. Instead of 0, I write x and then u of x is less than or equal to v of p, because px is less than or equal to 1. And similarly, it is less than or equal to v of q, because qs is less than or equal to 1. Okay, so I can adapt this part of the proof to the case. So the distinction is, let me present things in an ordered way. So I consider x in r plus n. I have to consider an arbitrary x in r plus n. Now, if for this particular x, px is 0 and qx is 0, then we have this inequality. This is what I have just proved. Okay? So now the remaining case is when not both of them are 0, but they are non-negative. So at least one of them, let's say the maximum between them, and the rest of the proof I wrote yesterday works well in this case, as you are going to see. So I consider x such that this holds. Okay, this is the second case. Let's say this is case 1, and now we go to case 2, which is the negation of case 1. Then, but still this x satisfies this condition. Then we have u of x less than or equal to u of x divided by 1 minus lambda px plus lambda qx. Do you know why? Because this denominator is smaller than 1 and u is non-decreasing. Okay, I have increased x, then u increases. And then I have here t and t prime. I'm going to use our assumption, which is now convexity of this function. So the variable is in the denominator. This is less than or equal to 1 minus lambda u of x divided by px plus lambda u of x divided by qx. Do you agree that this follows from the assumption that all these functions are convex? You agree, but I don't. Exactly. So I here, this is why I said, I don't know if you agree, but I don't. Because now I notice that this doesn't cover the case when both of them are 0. You are absolutely right. So again, we will have to distinguish between cases when one of them is 0 and the other no. So now, in fact, we will see what happens in that case later. So in fact, what we are assuming now is that the minimum, not the maximum, is positive. So both of them are strictly positive. Okay? We will see later if we can, what can we do when the case, when both of them, when one of them is 0 but the other is not. When both of them are 0, this is already solved. But, okay, the case you rightfully observed is also covered by this case, if I am not wrong, because, okay, suppose no. Suppose Px is 0, but Qx is not, then no, maybe not. So we will see later. If not, since this is published, I will look at the proof I have in this volume in honor to my friend Antonio Martinon, and let's see what happens. Okay, but now for the moment, assume that both denominators are strictly positive, and then P times P inner product this vector is 1, Q inner product this vector is 1, and then this is less than or equal to 1 minus lambda V of P, okay, This is one of the feasible vectors under P. So the value of the objective function is not greater than the optimal value plus lambda B of Q for the same reason here. And that's almost the case. No. I know what's happened. No, we need no distinction. I forgot to say that we are assuming, I didn't assume. So I forgot to say, so we divide the proof in two parts, but not distinguishing between X, what does it satisfy, but distinguishing between P and Q. So this proof goes without problem in the case of the maximum if both P and Q are strictly positive. Because then, in case 2, we are not dealing with x equals 0. Because x equals 0 falls in case 1. Then x is non-negative and different from 0. Then multiply with P or with Q, it is strictly positive as long as P and Q are strictly positive. Okay, so the proof would be finished if P and Q were to be taken only in the strictly positive orthon. Okay, because in this case, because X is an arbitrary feasible vector under this convex combination, then taking the supremum here over such X, we get V of 1 minus lambda P plus lambda Q less than or equal to 1 minus lambda V of P plus lambda V of Q. So if prices are strictly positive, we are done. But we need to consider the case when they are just non-negative. Okay? Is this clear? So now, so this case 1 is and case 2 are under the assumption that P and Q are strictly positive, and then in fact now, after seeing that we consider P and Q strictly positive, then here I could have, as I did at the beginning, assume that X is equal to 0. So the case X equals 0 is covered here, and the case X different from 0 is covered there. Okay, but now assume that P and Q are just non-negative. And then consider the all one vector. Then V of 1 minus lambda P, we are not going to deal now with U. We are going to do it directly with V. So V of 1 minus lambda P plus lambda Q is, because the previous result is equal to the supremum or the limit, as you prefer, for alpha positive of V of 1 minus lambda P plus lambda Q plus alpha E. This is what we saw, that this happens for every direction, even non-negative directions. So it happens in particular for E. So, and what happens with this right-hand side? V of 1 minus lambda p plus lambda q plus alpha epsilon for a given alpha is V of. So we just need this trick to go to the interior or the ortho. Okay? 1 minus lambda p plus alpha epsilon, alpha e, plus lambda q plus alpha e. Okay? And because p plus alpha e and q plus alpha e, thanks to E, has strictly positive components, are in R plus plus n, we can apply what we have just proved in the first part of the proof. So the convexity condition holds for strictly positive vectors. So this is less than or equal to 1 minus lambda V of P plus alpha E plus lambda V of Q plus alpha E. What is the relation between V of P plus alpha E and V of P? V is non-increasing, so P plus alpha E is larger than P, so V of P is smaller than or equal to. So we have less than or equal to 1 minus lambda V of P plus lambda V of Q. So every number entering in this supremum is less than or equal to that. Then the supremum, taking supremum, we also get this inequality, but the supremum is V of the convex combination. So in this way, we conclude that V of 1 minus lambda P plus lambda Q is less than or equal to 1 minus lambda V of P plus lambda V of Q, so that the convexity condition also holds for arbitrary non-negative commutative bundles. Okay, but we needed to use the previous result showing this property along lines of the utility function, which holds under regularity and continuity. Is the proof clear now? Yes? Thank you. So it's probably time to stop. Is it? If you have questions or comments, we'll continue talking about all these issues tomorrow morning.